This video will introduce how to analyze the timing of code. As you have seen in several of the examples, we have developed delay loops, and up until this point we have basically ignored how long those delay loops will last. In this particular lecture, we will learn how to analyze how long certain code takes to run and think about designing code to run for a certain period of time. So timing is very critical to microcontroller-based applications. You can think about the many places where clocks are used. You use them for sporting events, so you either are counting down or counting up depending upon the sport that you're talking about. So basketball in college has 20-minute halves, and you count down from that, and you need to be able to stop the clock when there's a stoppage of play. College football or professional sports, all of them have clocks. In soccer you count upward, in other sports you count downward. Cooking, things are critical in terms of timing. If you set your microwave to run for 2 minutes to heat up a dish, you want to make sure that it is in fact running for 2 minutes, not 20 minutes, not 2.5 minutes, but the amount of time that you set. If you have certain alarms that are supposed to go off after a certain amount of time, so you can think about an alarm clock in the morning needing to go off at whatever time you specify, or you could have other alarms that are set to go off based on certain times. So for instance, on my Outlook calendar I have certain events set up that alert me before it's time for me to go, and it's critical that my computer keeps track of the time properly so that it reminds me to not be late to these events. Data transmission is also very important in terms of timing. A lot of times you have certain channels and they expect data to be sent at a specific rate, and so you have to make sure that you are sending the bits of data across the transmission channel at the correct rate of speed, whether that be for wireless communication over a network, it could be for wired communication over, let's say, a landline telephone or those types of things. All of that data needs to be sent at the expected data rate. You can also think about different lights that blink, and you want to make sure that they blink at an appropriate frequency. So turn signals need to blink fast enough so that people are aware that you mean to turn. You can imagine if a turn signal blinks so slowly you didn't notice it, that could cause accidents. But also if it blinks so quickly that it's almost blinding or distracting to other drivers, that's not good either. And so the timing of that blinking is fairly well defined. For most automobiles, it's within a certain range of frequencies. You can think about Christmas lights and other holiday decorations that blink. You want to make sure that things blink at an appropriate frequency, not too fast, not too slow. You can think about different warning indicators that may come up. So for example, on my car, when I'm starting to run low on fuel, I have a light that comes on and it will blink to try to draw my attention to it, to remind me that I need to get fuel so I don't run out of gas. You can also think about the timing of various mechatronic systems. So if you're needing to turn on a motor for a certain amount of time, if you're needing to turn on an actuator, some kind of pneumatic or hydraulic for a certain period of time, you want to make sure that it's on for the right amount of time. Manufacturing especially has very critical timing. You want to make sure when you're thinking about automated manufacturing or even manufacturing where there are people, that the belt moves at the right rate of speed so that parts get to where they need to be, and all of the tooling is being able to be done at the right amount of time, and that you do move particular parts to the right location at the right time. And of course medical systems. So if you're trying to design something like a pacemaker for a heart, you need to make sure that you are properly timing things. Also, if you're thinking about collecting medical data, you need to make sure that you sample at an appropriate rate, appropriate frequency, and we'll talk a good bit more about such types of sampling later on in the course. The clock is what determines how fast your code executes, as we mentioned before, and the QL200 trainer kits that we are using in this class use a 4 MHz crystal oscillator as their clock. And so that means that you have a dedicated component that oscillates at a rate of 4 million times every second. each instruction cycle is actually divided down by 4 periods of the clock cycle. So most every instruction takes roughly 1 microsecond to execute, with some exception, and we'll talk about that briefly. I do want to, while we're talking about timing, introduce one more command that we haven't talked about before, and that is the NoOp, short for no operation. Some people call this a NoOp, and that is very useful when you're trying to create a specific delay. So this particular operation does not change your W register. It's not going to change any of your other special function registers other than the program counter just incrementing by 1 as it does with any line of code. Effectively, it does nothing. It would seem useless, but that allows us to delay a single clock cycle, which we'll see the importance of in just a moment when we start going through some delay loop code. If we want to talk about how long certain code takes to execute, we need to realize that most instructions take 1 clock cycle or 1 microsecond. Some other codes or commands that have branching take 2 cycles when there is branching. Things like your gotos, your returns, return literal and with literal and W, all of those take 2 cycles. And you can look at table 15.2 on page 236 in the data sheet to see more detail. And the following slides will be excerpts from that particular table in the data sheet for the PIC. There are some odd instructions that I do want to talk about that sometimes take 1 cycle and sometimes take 2 cycles. Things like increment f skipping of 0 and decrement f skipping of 0. Those, if you're simply incrementing and it does not result in 0 so you don't have to skip, when you're just doing the increment or the decrement, that takes 1. But on the occasion when it does get to 0 and you have to have not only the increment but also the skip, that will take 2 clock cycles. Similarly, the bit test f skip if clear or bit test f skip if set, when you do the bit test, if you don't skip, then that's 1 clock cycle. But in the event that you do skip, then it uses 2 clock cycles. So here are some of the commands that we've talked about thus far. And so you can see that most of them, most all your logical or arithmetic operations, take simply 1 clock cycle or 1 microsecond in this case to execute. You will notice what we talked about before with the decrement f skipping of 0 and increment f skipping of 0. They're noted in this chart as 1 and sometimes 2. That's what the parentheses 2 is indicating here. Here you notice that bit clearing and bit setting just takes 1 clock cycle. And here when you're doing bit tests and skipping, if you don't skip, it's 1 clock cycle. If you do skip, it's 2. And then down here, some of these commands we haven't talked about quite yet, but most of them we have. If you're just doing arithmetic or logic operations like adding or anding, then those are 1 clock cycle. When you're calling a subroutine, that takes 2. When you're going to a particular line, that takes 2. And then any of your returns also take 2. But other than that, each command takes simply 1 clock cycle or 1 microsecond. So how do we figure out the runtime? Well, it's simply a matter of bookkeeping. And so what you're going to do is look at all the lines of code and determine based upon the table whether those commands are 1 clock cycle commands or they're 2 clock cycle commands. And then what you want to do is think about how many times each of those lines of code will execute. So when you're going through, a lot of times code will only execute 1 line at a time and then it's done. In other cases, if you're in a loop, certain lines of code may be executed over and over and over again. And so you want to figure out how to trace through that logic to figure out how many times certain loops are running and to design your logic accordingly to get the specific time that you're interested in. And so there, all you need to do is multiply how many times a particular line of code gets executed by the number of cycles that it takes in cycle time to execute. So then you just simply add up the total for each line of code. Let's go through an example. So how long will the following code take to run with a 4 megahertz clock? Well, with a 4 megahertz clock, we know, remember, we divide by 4, so we've got a 1 microsecond clock cycle time. Here we have a call to a subroutine one of the things we do want to account for when we are thinking about how long subroutines take is that simply executing the call to the subroutine takes 2 clock cycles or 2 microseconds. So we know that that gets executed once, and that will take 2 microseconds. So we've got that. Now if we get down into this loop and think about how this is working, we're moving a literal 4 into W, then we're moving that over to count, then we're getting down into this loop, and we're decrementing count and going back to loop, and we keep doing that until count gets all the way down to 0, at which case we hit the return, and we go back and we'll go to the line after the call. So if we think about how that works, these two lines of code, the moving literal into W and moving W over to F, also only get executed one time, and those are 1 microsecond commands. Now if we get down into this decrement F skipping of 0, that's the trickiest line of code that we have in this example. And so in this case we need to think about how many times will this code get executed where we just decrement, and then how many times will it get executed when we will skip. And so our count is initialized to 4 here, and so we start out and we run this starting at 4 decrementing to 3, that's once, and we're going to go to this loop, we're not going to skip. Then we are at 3, we're going to decrement to 2, so that's twice, and we didn't skip. Then we're going to be at 2 decrementing to 1, that's 3 times, and we didn't skip. And then we're going to be at 1 decrementing to 0, and that time we will skip. So what did we see happen? We executed 3 times without skipping and 1 time with skipping. So that particular line of code gets run a total of 4 times. 3 times it takes 1 microsecond, and the last time it takes 2 microseconds. And then our goto, how many times does that get executed? Well, that gets executed every time our decrement F skipping of 0 did not skip, which would be 3 times. And remember, a goto takes 2 microseconds. So that's going to be 3 times 2 microseconds. And then the return statement here at the end of the subroutine will only be executed once for each subroutine call. So that's going to be once times 2 microseconds. Now, if you do the arithmetic and simply add all of these up and do your multiplying out, that works out to be a total of 17 microseconds. Now, let's look at another example. In this case, our code looks nearly the same as what we had before that took 17 microseconds, but we've added a NoOp right in here, or no operation, right at the beginning of our loop. And so now, let's look at what's happening. Well, our call is being executed once, and so that's taking 2 microseconds. Then we get down in here, the same issue is happening. We're moving a 4 into W and moving that over to count. Each of those get executed once. And now inside of the loop, we execute the NoOp, which takes 1 microsecond. Then we decrement, and if we aren't decrementing to 0, we don't skip, and we go on to this goto loop, which will allow us to simply go back and forth until our count variable reaches 0. So our NoOp, if in this case count starts at 4, our NoOp gets executed once, count is still 4, we decrement count to 3, we don't skip, and we go back up to the loop. Then we execute the NoOp again, so now it's run twice, and we had decremented to 3, this time we're going to decrement to 2, and that is not 0, so we're going to go back up to the loop, and we've now run the NoOp a 3rd time, and so from there we will decrement the count again, and what you will notice is that the NoOp runs as many times as we go through the loop. And so in this case we go through the loop 4 times. We go through the loop count times, and so our NoOp will be executed 4 times 1 microsecond. Our decrement, skipping of 0, and our goto loop work exactly the same as in the previous example. So our decrement is taking 3 times 1 microsecond, and the last time is taking 2 microseconds when it skips, and our goto, just as in the previous example, is executed whenever we did not skip with the decrement F skipping of 0, and then finally we hit the return. So our goto gets executed 3 times, each of those taking 2 microseconds, and our return gets executed once, and a return takes 2 microseconds. So if we add all of this up, that works out to be 21 microseconds. So that little NoOp allowed us to add 4 microseconds. Typically, the way you structure delays is using a for loop. Remember, in for loop programming, you go through and you set up a value and you can decrement it until it gets to 0, or you can set up a value and keep incrementing it until it overflows. And so you will want to set how many times that loop runs, and you can use some algebraic techniques to determine how many passes through the loop are needed to get the desired delay. So here is another way to look at it, is what is the longest time that this delay code can run for any hex value. And so this will be an exercise we will do in class. You might want to think about that. And I just represent number sign, number sign. So any valid 2 hexadecimal place, 2 hexadecimal digit value is valid for our literal value here. And so we want to see what will happen. And you might not be surprised to know that the largest literal value, FF, is what makes this run the longest. And so this will be one of your in-class exercises this week, and we'll go over this a little bit more. So what can you do if you want longer delays than what you can get with the previous example? If you worked out the previous example, you know that while it delays for a little while, it's really not delaying for very long. Well, you can do one of 2 things. You can add some more no operations, which adds you a little bit more time, or you can nest some loops, in which case you're executing one loop as an outside loop, and then you've got another loop as an inside loop. Let's see an example of that. Here's some nested loops. So we're going to call this subroutine delay, and it's got delay labeled at the top, return at the bottom. And what we're going to do is we're going to keep track of 2 counters, a counter 1 and a counter 2. It's going to be, both of them are going to be initialized to FF, and then we're going to get down into the inner loop. We're going to have a couple no operations to waste some time. Then we're going to decrement our counter 2, and if it's 0, we'll skip, but for the most part it's not going to be 0. We're going to go back to inner and keep hitting NoOp, decrement until our counter gets all the way to 0, at which point you will skip down to here and you will decrement counter 1, and then you will skip, if that got to 0, back to return, and the subroutine would be over. If this doesn't get all the way to 0, then you can go back and do a go to outer, and that will reload your counter 2 value. And so you'll just keep going and doing this until both of your counters run down to 0. So in lab next week, you're actually going to be building a digital stopwatch, and you're going to be using your 7-segment displays on the trainer kit for that. And so you will need to create a delay loop that will last for 1/100th of a second. And we'll give you some practice doing some timing with the in-class exercises this week. So at each pass through the loop, you can either increment or decrement the value in your loop, but what you're going to do is you're going to increment the value on the counter in your hundredths of seconds, and then if that needs to overflow, you're going to increment your next space, and so you will represent 10 minutes, 100 minutes, 10 seconds, 1 second, tenths of seconds, and hundredths of seconds on your display. So with that, thank you very much for watching, and I will see you next time.